The last thing I want to talk about within our Chapter 1, Section 2 is our set notation as well as absolute value and opposites. So again, let's go over some vocabulary here. So first, we're talking about set notation with roster form versus set builder form. An ellipsis is a listing of three dots, indicating a continuation of the same pattern. We've seen that already. A set is a very simple definition. It is a collection of objects. Now, within a set, we have members or elements. Those are the objects within a set. We have this E kind of looking symbol that means that this is an element of that set. So for example, we have 3 and this symbol is in the set that's listed here. And that just indicates that 3 is a member of this set. If I look at the set, I say, yes, I have the number 3. But I can also have, hey, it's not a part of this set. And so I could give and say 4. And I have the same symbol with a slash through it. And 4 is not a member of the set of 1, 2, and 3. So I see 4 is not in that set, but 3 is. Roster form is just the listing of the elements in a set in brackets. And then we also have set builder notation, where it describes the elements in the set but doesn't list them. This is usually for when we have sets that are too big to list. It would be too cumbersome to write all of them down. For example, to try and write the elements of all even numbers, it may be a little more complicated than we need to be. So set builder notation describes that set. And so here's an example saying, so X such that, that's how we write this out. So X such that X is a whole number less than 3, and there's the description. So we could identify our whole numbers that are less than 3. So less than 3 would be the number 2 and the number 1 and 0, and those are all the numbers in roster form that are whole numbers less than 3. An empty set or null set is symbolized by either empty brackets or this circle with a line through it. And so if we look at set builder notation, we say X such that X is a month with 32 days. There are no months that have 32 days in them, and so we would write it as an empty set. So let's go ahead and write each set in roster form and then another set in set builder notation. So the first thing we'll look at is X such that X is a natural number greater than 100. And so we're looking at our starting point. We want greater than 100. Well, the first natural number that is greater than 100 is the number 101. And the next number that is natural, greater than 101, is 102. And we just need to include enough numbers here until we get the pattern. And then we can use our ellipses to indicate that this pattern is continuing. Next, we want even integers between -4 and 4. So we want to look at the numbers between 4 and 4 that are integer values. And so the next number between -4 and 4 is -3. Then -2, -1, 0, 1, 2, and 3. And those are all integer values between -4 and 4. And then we want a whole number less than 0. That's what this should say, less than 0. Okay? I want you to think about that. A whole number less than 0. Well, if we look at our list, well, whole numbers, there is nothing less than 0 in the whole numbers. Everything's greater than 0. We could look at our number line and see there are no whole numbers over here. And so since there is no whole number less than 0, we can indicate it using an empty set. Next, we want to write them in set builder notation. So remember, set builder always starts with X such that X. It doesn't have to be the variable X. It could be any variable, but we usually use X. X such that X is, and then we describe it. So we want to think about it. And sometimes there's some variations that we could do, but we want to try and get it in the simplest terms possible. And so one way we could look at this and say, all right, well, we have whole numbers. Okay, so we have whole numbers. We could write it one way as we see our starting point is 0, which is a whole number. If we go lower than that, we don't have whole numbers anymore. And then we go up to 5. So we could say that X is a whole number less than 5. Or I'm sorry, not 5, less than 6. So So we have all the whole numbers less than 6, and that includes 0, 1, 2, 3, 4, and 5. We could also say is a integer between -1 and 6. We could say is, yeah, so those are probably the only two that we could do, an integer between -1 and 6, or a whole number less than 6 is the only way to include those without including any extra values. Again, we've got x such that x is, and it looks like we have integers, not just whole numbers or natural numbers, so we need to include integers, and it continues in the negative direction. So x is an integer less than 2. You could also say less than or equal to 1. That includes the 1, but that's a little bit more wordy. So if we say less than 2, well, it's a shorter sentence for us to have to write. All right, this one's a little interesting. We've got natural numbers, whole numbers, integers starting at 45, but we skip every 5 values. Okay, so since we're skipping every 5 numbers, it looks like we're looking at numbers that are multiples of 5. And so we'll want to write out that x, such that x is and we could say whole number, we could say natural number, we could say integer. It's all going to be included in there. So let's just say whole number that is greater than, so we want to go one multiple less than 45, greater than 40, and a multiple of 5. Okay, so we have that pattern that we need to follow. Absolute value is our next topic we're going to talk about. And I mentioned it a little bit in an earlier unit. Absolute value is a real number's distance from 0, so how many units we can find it from 0. It's denoted by the vertical bars, where a is any real number. Distance is always non-negative, so that means absolute value has to be either positive or 0. You can't walk -5 feet. That's 5 feet in a certain direction. And so absolute value measures distance. And so here we have the difference between the absolute value of -4. Well, it is 1, 2, 3, 4 units from 0. And then we also look at the absolute value of 4 and 1, 2, 3, 4 units from 0. So we look at the absolute value and say, okay, well, whatever's in the vertical bars, once it's simplified, we make it positive. So the absolute value of 3 is 3. The absolute value of -1/7 is 1/7. Now, we have the absolute value of 2.7, and then we want the opposite. We want to make that value negative, so we still end up with -2.7 because the negative is on the outside. Same thing with example D. -8, the absolute value of -8 is 8, and then we want to go ahead and make that value negative when we're done. And 0 is its own absolute value. It is no units from 0 because it is 0. Lastly, we've got opposites and double negatives. So opposites, also known as inverses, are numbers that are the same distance from 0, but on opposite sides of 0. And so we can see if we have the same absolute value, then those numbers are opposites. The opposite of a number is always going to be a different sign, and this plays into our double negative property. So for any number, if we have a double negative, it changes it to the positive. And so if we take the number and its opposite, we'll always get that positive. So let's go ahead and write the opposite of each number, 6.5. Well, the opposite of 6.5 is going to be -6.5. Our number is a, so the opposite is -a. So if we replace 6.5 with a, the opposite becomes -6.5. Now here, b, a, is -2/3. So the opposite is -a, which means if we take -2/3 and substitute it for a, now we're applying that double negative property. The double negative makes it positive. The opposite of -2/3 is +2/3. Same thing with -4. The opposite will be 4. And then for the absolute value, well, we're going to simplify that part first. So the absolute value of negative 3.5 is 3.5. And then we want to go ahead, and that's the value of a. We want to go ahead and plug that into our negative a, and now we get negative 3.5.